I'm Daiji Kawaguchi, Dean of the Graduate School of Public Policy at the University of Tokyo. As just mentioned, my specialty is labor economics. One of my main areas of research is understanding what actually shapes the way people work. As we saw earlier with the introduction to Matlantis, AI is changing the very nature of intellectual work across a wide range of fields. Naturally, that leads to the question of how this is actually going to affect the way we work. Some say it will lead to job losses, while others argue it will actually boost productivity, increase employment, or even raise wages. There's actually a lot of research being done right now in this area. Today, I'll be talking about artificial intelligence, or AI. But of course, robots are a similar type of technology, in that both robots and AI contribute to automation. There's a lot of public interest in how AI and robots might affect the future of jobs, labor productivity, and wages. And economists are doing a lot of research to try and answer these kinds of questions. I was thinking about how best to approach today's talk, and I'm not sure if this is going to work. But you're all grad students, meaning you're all researchers. Or researchers in the making, perhaps. In that sense, I figured you might actually be more interested in learning how we arrive at the answers. I imagine some of you are in the social sciences, but considering the University of Tokyo overall, and that you are all pursuing PhDs, I'm guessing a good number of you are in the natural sciences or engineering fields. So I thought it might be interesting to talk about how social scientists, specifically economists, actually go about conducting research using AI as an example. Recently, I co-authored a paper with 3 other researchers on what happens to productivity when taxi drivers use AI. One of the co-authors was a former grad student at the University of Tokyo. And all 3 of them were my colleagues at the Graduate School of Public Policy. The focus of the paper was to study the impact of AI on labor productivity. So what we wanted to do was look at how labor productivity changes when AI is introduced. It's a very simple equation, with labor productivity on the left-hand side and AI as a variable on the right-hand side. The goal is to estimate this kind of model. Now, this AI variable on the right-hand side is what we call an unobserved variable. It takes the value of 1 when AI is used and 0 when it's not. So once we include this variable, the beta becomes the parameter representing the effect of AI use on labor productivity. We want to estimate this, and we're predicting that beta is likely positive, that using AI will increase labor productivity. The goal is to keep going until we figure things out, including how large of a number beta actually is. Conceptually, this all makes sense. But once you try to actually do it, you run into a number of hurdles. One challenge is the data itself. We want to compare labor productivity when AI is used versus when it isn't. But to do that, we need to find data in which the use or non-use of AI has actually been recorded. Another issue is with labor productivity itself, which, as many people point out, is notoriously hard to measure, especially for white-collar workers. In our case, we were looking at taxi drivers who are generally considered blue-collar workers, but still. Measuring labor productivity isn't exactly straightforward. And we have to think about what data we can find to measure these kinds of metrics. And even if we do manage to find data that includes both labor productivity and AI use, things still aren't that simple. The tricky part is that AI use isn't randomly assigned. In reality, the people who use AI are the ones who want to use it. Meaning we have to think about what kinds of people are more likely to want to use AI. There's also the question of timing. When exactly people turn the AI on? Since it's pretty unlikely that anyone is being forced to turn AI on or off. We're usually dealing with situations where those who use it are choosing for themselves when to use it. When people are the ones choosing to turn AI on or off themselves, figuring out how to estimate this beta parameter gets pretty tricky. But figuring out what to do about these difficult parts is our main job as empirical economists. So I'd like to use the example of the taxi drivers to explain this. ChatGPT was released in November 2022, but AI had already been introduced in various areas even before then. And we had already been interested in figuring out how AI affects productivity. The issue, however, was the lack of data. But as it turns out, we had the opportunity to speak with an executive at a major tech company who told us during the meeting that they were planning to integrate AI-based navigation software into their taxi hailing app. As you probably know, most taxis these days are equipped with tablets, usually provided by specific companies like Go, that are mainly used to receive ride requests from passengers. As for what the AI actually does, it uses patterns in past ride data and applies machine learning to figure out where passengers are likely to be. Based on that trained data, it suggests which direction the driver should head to increase their chances of picking up a passenger. Normally, with GPS or car navigation systems, you put in a destination and it guides you there. But this is navigation without a set destination. The AI navigates by suggesting areas where the driver is more likely to find passengers, based on things like the time of day or the surrounding conditions. Drivers can turn this AI on or off depending on their preference. As for what the data actually was, since every ride is recorded, we received detailed data that included the start and end times, and latitude and longitude for each period in which each taxi was vacant. In December 2019, right before the start of the COVID-19 pandemic, We were provided with data from their field experiment in Yokohama. We also received data from October to November 2019 to estimate the baseline. So ultimately, our analysis was based on 3 months of data, from October through December 2019. In terms of the data we used, our unit of observation was each vacant driving segment. Each record of a vacant driving segment contains the driver's ID, the start time, and latitude-longitude of when the car became vacant, and the end time and latitude-longitude of when the vacant period ended. Alright, so you might be wondering what this talk of vacant driving time has to do with labor productivity. Well, the reality is that for taxi drivers, about half of their working hours are spent driving a vacant car. That means the time they spend in a vacant car, cruising around until they pick up their next passenger, is essentially the inverse of labor productivity. In other words, the shorter the vacant time, the higher the productivity. So, vacant time can be seen as an indicator of labor productivity. Our idea was to estimate the impact of AI on productivity by seeing how much the AI system reduced that vacant time compared to when it was not used. Some of you might be working in medical statistics, so this may sound familiar. But we treated the time from the start to end of a vacant drive as survival time and applied survival analysis. In typical medical statistics, you usually have a treatment group and a control group defined at the start. What's trickier in our context, and in the survival analysis we conducted, was that the AI navigation system could be switched on midway, meaning the treatment could kick in after observation had already begun. The data came from several taxi companies and was comprised of driving logs from 557 drivers. There's some repetition here, so I'll skip over some things. But the last bullet point is actually quite important. Even though the AI was available, only about 5% of all vacant drives were conducted with it turned on. And at the driver level, fewer than 40% of drivers ever used the AI at all, meaning the system was used less than we expected. Why wasn't it used more often? Well, part of the answer becomes clear when we look at the results. To dig a bit deeper into the difficulty of identifying causal effects, one common point made about social science data is that, because it's often non-experimental, it's harder to estimate causal relationships. But what does this actually mean in practice? In a controlled experiment, you could forcibly switch the AI on or off for drivers. But most social science data isn't derived from controlled experiments. There's a specific moment when the AI gets turned on, and it's the driver who decides to do it. And who are the drivers that choose to turn it on? They're the beginners. Experienced drivers already know where to go to find passengers, so they have little incentive to switch it on in the first place. But new drivers will turn it on. The problem is that when you do a naive analysis of this data, you'll see that the drivers who switch on the AI tend to have longer vacant times. So even though our expectation is that beta would be negative, meaning turning on the AI would shorten vacant time, a simple look at the raw data might make it seem like AI use is actually leading to longer vacant times. The problem with this is that it may appear as though AI isn't improving productivity when it actually is. Another factor is time of day. When did drivers tend to switch the AI on? Well, there are plenty of passengers at 11 p.m. on a Friday night, for instance, so drivers generally don't bother turning it on then. Conversely, when passenger demand is low, that's when the AI tends to be used. As a result, the times when the AI is on are the same hours as when vacant times already tend to be longer. This can make it appear as if using the AI is actually reducing productivity. The same applies for location. Naka Ward is the main downtown area in Yokohama City. But there are also suburbs like Aoba Ward. And that's where drivers are more likely to use the AI. They rarely use it in Naka Ward, since they'll be able to pick up passengers regardless. But they'll turn it on when they go to Aoba Ward. In short, whether it's the driver's skill level, the time of day, or the location, a simple analysis without considering these factors will find that the hours with AI use tend to have longer vacant times. This makes it difficult to accurately estimate the effect AI has on reducing vacant times. The first step in addressing this problem was to account for the fact that each driver has their own baseline, alpha, for vacant time length in our estimations. We also estimated models that allowed for variations in baseline vacant time by combinations of day of the week and time of day, and allowed for the baseline vacant time to differ depending on the location where the vacant period began. This approach is called fixed effects estimation, and by using it, we found that it became possible to identify a causal relationship. In addition, we thought about what factors might determine whether AI is used or not, in a way that is essentially random. Our thinking was that the destination of each passenger is likely to be random. And if the previous passenger asked to go somewhere completely unfamiliar to the driver, the driver would likely use the AI for the next vacant period. Because the previous passenger's destination is random, we can focus on the AI on-off variation caused by that randomness to estimate its effect. By combining these different methods in our analysis, we estimated the value of beta, that is, how much turning on the AI reduces vacant time. These were the results. Using fixed effects estimation, we found that turning on the AI navigation system reduced subsequent vacant time by about 5%. A 5% reduction in vacant time means an increase in labor productivity. We observed a similar result when we applied a combined approach, fixed effects estimation with something called instrumental variable estimation, using the randomness of the previous passenger's drop-off location. So far, this figure, the 5% reduction, represents the average effect. But we were also interested in whether this productivity boost might vary from driver to driver, and so we carried the analysis further. As I explained earlier when discussing the data, we also had driving records for October and November. From these, we could identify which drivers had longer vacant times originally. We classified drivers in the lower half of the skill distribution as those whose vacant times in October and November were above the median. For this group, the AI reduced vacant time by 7.2%. For the upper half, who were either experienced or more skilled regardless of their level of experience, who knew where to find passengers and who already had shorter vacant times, the reduction in vacant time from AI use was only 2.5%, and the effect was not statistically significant. In other words, the productivity gains from AI were observed only among drivers of low skill levels. So, why did we get this kind of result? If we think about the task the driver, or the AI, is performing, it's essentially learning patterns from past driving data to predict where passengers are likely to be. This is the task the AI is doing. Experienced drivers already know, from their own accumulated pattern recognition, where to go to find passengers. Which is why, for them, adding AI doesn't improve productivity. By contrast, for new drivers who have just started off and have no idea where to go, turning the AI on actually gives them useful guidance on where to find passengers and can be quite effective. So when you think about it, the outcomes make sense. When we began this research, we were given the opportunity to interview taxi drivers in Yokohama City. We interviewed them in a kind of rest area where taxi drivers gather, and as you might expect, their answers varied. We asked those who had used the AI about their experiences. Some said it was extremely helpful, and these were mostly drivers who had only recently started. Others said they turned it on, but it only told them things they already knew. And those tended to be the more experienced drivers. So the results we got were consistent with what we had heard in these interviews. We can also break down the AI's effects by skill level in more detail. On this chart, the horizontal axis shows the skill index, or standardized measure of driver skill. A value of -1.5 means the driver's skill level is 1.5 standard deviations below the mean, while +1.5 means it is 1.5 standard deviations above the mean. The vertical axis plots the scale of beta, which is measured in natural logs. A value around 0.07 corresponds to roughly a 7% reduction in vacant time, or minus 0.07 in log points for the lower half of drivers. As we move toward higher skill levels, the effect size decreases and becomes statistically indistinguishable from zero. The shaded area represents the 90% confidence interval. Since zero falls within this interval, the effect is not statistically significant. Those were the results we got. So, what can we take away from this? The results suggest that the ability experienced workers have to make predictions based on experience can be replaced by AI. This experience-based predictive ability is thought to be one of the main factors that define high-skill work in many professions. In that sense, these results suggest that AI could help raise the productivity of lower-skill workers in other occupations as well. Earlier, I mentioned the question of exactly whose productivity AI will improve in the field of science, and I think this is a fascinating topic. It's quite possible that the biggest effects occur for people who have only just started. Of course, this is something we can't know without testing it. Perhaps we can collect data from this Spring GX program, analyze it, and see which types of people can benefit from AI. That theory might be proven correct. This study actually began in 2019 and was already completed before the fall of 2021. But it was while we were conducting this research that ChatGPT came out in November 2022 and led to explosive growth in research on this topic. For instance, there was a service whose customer service operations were located in the Philippines. The customer service there already had a speech recognition system. And researchers introduced AI that, once the customer's speech was transcribed, would guide the agent toward an appropriate response. In this paper, for this computer-related customer service, the time needed to handle inquiries was reduced, and customer satisfaction ratings afterwards also went up. Another paper, this one focused on writing skills, had human evaluators measure participant writing skills, then had participants use AI to see whose scores improved. In both cases, the common finding was that AI improved productivity for lower skill workers. The first of these papers was published in the Quarterly Journal of Economics, which is probably the top journal in the field of economics. The paper on writing was, I believe, published in Science, a general academic journal. As for our own paper, speaking candidly, the fact that it was unfortunately set in the context of taxi drivers, I think reduced the impact of it somewhat, despite us essentially finding the same sort of result. That being said, the finding that AI can raise the productivity of lower-skilled workers is actually quite different from the patterns seen in much of past technological progress. Take robots, for example. Robots have a tendency to replace blue-collar jobs, leading to the loss of work for lower-skill workers. This means that the introduction of robots has tended to widen economic inequality. Similarly, it had long been understood, almost to the point of consensus, that information and communication technology, ICT, primarily boosts the productivity of already highly productive workers. This is sometimes referred to as skill-biased technological change. or technological advances that disproportionately raise the productivity of already high-skilled workers. Robots and ICT are thought to be this sort of technology that widens inequality when there are technological advances. When it comes to AI, however, the existing research so far suggests that it may be a technology that actually reduces inequality. And if we think further about the social implications of this AI technology, and this is one thing that is actually happening now, is that taxi driving, which was once a job only for those who were experienced, became easier to do for various kinds of people, including young people and women, allowing a broader range of demographics to drive taxis. This connects to broader themes of diversity and inclusion. Another point, which came from the executive at the taxi company, and which I found particularly interesting, is that taxi drivers generally work on a commission basis, taking about 50% of their fares as income. This is because, if you pay taxi drivers a fixed salary, there is the issue of moral hazard in that they may slack off. Since companies can't monitor the drivers, they avoid paying a fixed salary. But not paying a fixed salary and paying on commission discourages people who are risk-averse from entering the profession. It's a well-known finding that women tend to be more risk-averse than men. What this executive was saying was that housewives, for instance, are particularly reluctant to become taxi drivers because of that risk. One possible outcome of introducing this AI technology is that companies could adopt new kinds of contracts. For example, one that pays a fixed salary if the driver follows 90% of the AI's suggested routes. We'll pay you a fixed salary, so please drive according to the AI's suggested routes. With such a contract in place, even younger drivers or women who are more risk-averse could become taxi drivers as well. This is one way technology could really fundamentally change how society works. This is admittedly a bit of a stretch from the perspective of our study, but it's still a possible implication that I think is worth noting. Since there's a little time left, I'd like to touch briefly on the last slide as well. There are actually quite a lot of researchers writing micro-level empirical economic papers like this. It may seem like you can immediately run an empirical analysis as soon as you have the data, but in reality, it's quite difficult. Because what we generally aim to estimate is the causal effect of X on Y. For instance, one of my co-authors, Hitoshi Shigeoka, is doing work estimating the effect of hay fever on traffic accidents. So X would be pollen, and Y would be traffic accidents. Economists study all kinds of such relationships. I think there are 3 conditions that need to be met for this kind of study to be successful. The first is that the causal effect of X on Y must be economically interesting. For instance, what is actually important with regards to the hay fever coefficient? If you wanted to address hay fever itself, you would probably have to replace a lot of cedar trees, and that would be costly. We can figure out the cost of that, but how much value is gained from getting rid of the cedar trees and eliminating hay fever is hard to put in monetary terms. But if you do Shigeoka's or other studies properly, you can learn, for instance, that it reduces traffic accidents by this specific amount. We already have an understanding of the economic value of preventing a single traffic fatality. So by combining these, we can calculate the economic benefit of reducing cedar pollen. With that, you can assess whether a policy like replacing cedar trees is economically reasonable. In this sense, when you show the effect of X on Y, it had to connect to something. It can't be the kind of research where people say, well, so what? You need to choose a research topic where, once you've found the answer, you can clearly say, this was meaningful because we were able to find this out. The second condition is that the data should be large scale. This is especially true in the social sciences and economics, where there are countless factors that can affect Y. For example, there are a huge number of things that can influence the length of a vacant drive for a taxi. Because of that, the data are full of noise. We need large datasets to be able to detect average tendencies. This is why large datasets are crucial. Another point is that measurements must be accurate. If Y isn't measured precisely, that adds even more noise, making estimation more difficult. So what counts as large-scale, accurately measured data? This was true in our case with the taxi drivers, but operational data used for business purposes, which usually accumulates automatically, tend to be both large in scale and highly accurate. That is why obtaining and analyzing such datasets has become increasingly important. The final condition is using an appropriate identification method. You have to think carefully about what factors are driving the variation on the right-hand side, and be able to present a convincing argument as to why that is. These three factors, an economically interesting relationship between X and Y, good data, and a strategy that allows for proper identification, must be met for a study to be a good one. And in fact, you can often predict whether they're met before you even start the analysis. That's why, before beginning a study or data analysis, you need to think very carefully about whether all three of these conditions have been met. Research rarely turns out as we expect, but at the very least, you need to start from a point where these three conditions are satisfied. Otherwise, you'll run into trouble later. This is something that's probably true of other fields as well. But research design really matters. Before you start, before you take action, it's important that you predict what kind of results you expect to see, and establish a solid, consistent research design. Often, when I give advice to new graduate students, I find that they're interested in the first point, in that causal relationship. I'm interested in how X affects Y, but then when I ask what data they'll use, or how they'll do the identification, oftentimes they don't really have an answer. And in reality, these second and third points are so incredibly important. If you look at how research is actually done in practice, it often works the other way around. You start with data, and notice there might be a way to identify something interesting. What we often call a natural experiment, where there's some randomness in the variation of the right-hand variable. And you have the data and identification, and you think about what question you can answer with that setup. In practice, there are research topics in these settings, and how they come to be decided is that there's good data there and an interesting experiment. And I think what happens is that the research develops from there. That's all for today's lecture.